We are on the air, hocam. I think we should start.
Okay.
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 Hi, everybody. Welcome to Sabancı University IEEE Math Society's first seminar. It is me, Taha, and today we are here to join our first seminar, which is Introduction to Ordinal Numbers from Professor David Pierce. Hi, hocam. Welcome, firstly.
Okay, thank you. Teşekkürler.
At the beginning, I will introduce Mr. Pierce briefly, and then I will leave the word. Okay. David Pierce got his BA degree from St. John's College and then continued his PhD studies in Maryland University. After a few postdoctoral studies in Mathematical Science Research Institute and McMaster University, Canada, he came to Turkey as a part of ODTÜ, and for more than, I think, 8 years, he is part of Mimar Sinan University as a professor. Again, welcome, hocam, and I am right now letting you the words.
Okay, thank you. Yes, I will. Okay, you have my little picture, and I will write on the whiteboard. Okay, this is about ordinal numbers, and as much as possible, I want to talk about them by analogy with the real numbers. And I want to start by considering, well, what is the first mathematical, or what are the first things, the first mathematical things that we do in life? And I mean, I guess one obvious, maybe I'll just take some time. What do we do first? Well, in math, okay, in life somehow. And I guess there's counting is kind of an obvious mathematical thing we learn to do, but maybe also drawing lines. This is somehow mathematical on a basic level. And I think they're different. I mean, sometimes counting is about discrete things, and okay, but a line is continuous. So I guess from counting, we learn arithmetic, adding, multiplying. From drawing, okay, I guess this is geometric, or okay, geometry, let's say. And beyond these, in mathematics, okay, let's say there is analysis. I mean, okay, calculus, the notion of convergence, limits, such things. I mean, both arithmetic and geometry are somehow ingredients. But normally, I guess analysis, okay, analysis is based on the real numbers. I want to look at the analysis of the ordinal numbers. Excuse me, my connection may be unstable. I mean,
yes, a little bit.
I have an alternative connection. Sorry. Okay, so okay, let's try to continue. What here? Ordinal ON stands for the ordinal numbers, and this is mainly what I want to talk about, but by analogy with the reals. Well, where do the reals come from? I mean, okay, these counting numbers, okay, 1, 2, 3, and so on. Then these counting numbers, then in school, okay, you learn you can add the 0, you can start counting with 0. You get negative numbers. Fine, so that is, if the counting numbers give you n, if you add 0, you get, I will call it omega, the set of natural numbers. If you add the negatives also, you get the integers. But then from that, you fill in with fractions, you get the rationals. But then beyond that, the reals. Now I will go to another page here. Well, okay, maybe, can you see the bottom if I draw in the, somehow the rationals fill out a line, but the reals also fill out a line. So my question, what's the difference between the reals and the rationals? Okay, I go to new page, I think. Okay. So what's the difference? Between the rationals and reals? Because I think most of high school algebra can be done with the rationals, but calculus needs the reals because what? Well, for one thing, you don't have, not all square roots belong to the reals, but beyond that, you have the transcendental numbers like pi or e. Now, so I also, we can understand the real numbers as the set of, so every real number is a limit of Cauchy sequence. In Q. Right, limits of Cauchy sequences. I mean sequences so that the common, the differences between entries become as small as you like. But these may not have a rational limit, but they have a real limit. But an alternative way to understand the reals is that every real number is the supremum, or the real numbers are the suprema, the least upper bounds of bounded non-empty subsets of Q. And okay, this is worked out in calculus and analysis. Now, so suprema, least upper bounds. So I mean, in particular, if you take, here's the rational number line, and if you break this into two pieces, then there may be no rational number that makes the break. For example, the square root of 2 might make this break, but some real number will make this cut. it could go here or here, but okay. This is Dedekind's idea, the Dedekind cut. So anyway, we're talking about ordinals. So let's see here. I'm going to say the class of ordinals. This is the class of all, same idea, suprema of subsets, but okay, still subsets of ON. Okay, this is a bit strange. Okay, we'll have to explain this. Let me go to another page. But also, the class of ordinal numbers the closure of the set of natural numbers under taking suprema and successors. Okay, what do I mean? Let's be more precise. So there, there's a least ordinal number, 0, which is the least natural number. There is every ordinal alpha, well, there, as with the counting numbers, with the natural numbers, there's always a next one. So every ordinal alpha has a, well, let's call it a successor, called alpha prime. Namely, okay, this is the minimum element, the least element of the set of xi. This is like the Greek x. This will always stand for an ordinal. The set of xi that are less than, greater than alpha. So there are ordinals greater than alpha, and the least of those is the successor. But sorry. So with these two rules, I mean, if we close under these two rules, well, this is ordinary counting. Start with 0, then you take a next one and the next one and so on. You get the natural numbers. This, so this much gives omega the set of natural numbers. But now what we do is say, look, for example, take all the natural numbers. Let's just say, well, I mean, in ordinary calculus, you fill in the gaps by taking fractions and cuts. Now we're going to say that there is some number bigger than all of the natural numbers. So let me go to another page. So the third rule, what we said, we'll say every set A of ordinals has a supremum. This will be our rule for generating ordinals. So, for example, I mean, the supremum of the empty set, well, every element of the empty set is less than every ordinal because there are no elements of the empty set. Therefore, the supremum of the empty set is the least ordinal. The least upper bound of the empty set is the least ordinal, which is by definition 0. But if A has, of course, if it has a greatest element, that's the supremum. If A has a greatest element beta, then of course the supremum of alpha is beta. But there's an alternative. If A is non-empty and has, well, actually, if it's empty, it has, well, I'm sorry, if A is empty and has no greatest element, well, we still assume something is greater than everything, and so it still has a supremum. Then but this is a new ordinal, not an A, and this is called a limit ordinal. And general, the least limit ordinal we declare to be omega. This is the smallest, this is the name of the smallest ordinal, which is greater than all of, greater than each natural number. But then we keep going. Now, go on, okay. So we said, okay, by definition, omega is the set, but I mean, 1 is the successor. We can define it to be the successor of 0, and 2 is the successor of 1, and 3 is the successor of 2, and so on. Omega then these are all successors. Omega is the first ordinal that's not a successor. Omega is the set of, well, okay, again, okay, sorry, I just said that. Omega, but this is then the set of all ordinals xi which are less than omega. So these ordinals are elements of omega, but they're also in the ordering less than omega. So in general, in fact, we can make this definition so that the 3 properties of the ordinals are satisfied. In general, for every ordinal alpha, we can define every ordinal alpha as the set of ordinals which are less than alpha. So in other words, 0 is the empty set because no ordinal is less than 0. 1 is the set that contains only 0. 2 is the set of lesser ordinals, and so on. Okay, I mean, this is the definition you can give in set theory in order to obtain the ordinals in the way that we want. And in general, going to a new page, also, yeah, the successor of alpha prime. Okay, everything in this is bigger than alpha, so everything less than alpha is an alpha prime, but there's one more element, namely alpha itself. Okay. If A is a set of ordinals, then the supremum, well, just think, if A is, you have A contains a bunch of ordinals. Well, you can think they're just, 0, 1, 2. They go a certain distance. The supremum should contain everything that's in one of these. In other words, the supremum is the set of all ordinals xi, such that for some epsilon, for one of these epsilons, not epsilon, eta, sorry, xi, well, is less than or is in there. But this is, by the set theoretic definition, this is the union, if you've seen this. I probably won't use this again, but this is how you can obtain the supremum of a set of ordinals in set theory. Now, so ON, it's this sequence like the natural numbers. Okay, so you get all, these are all, there's 0, and then the successors, and then, okay, somehow we obtain a new ordinal, omega, called omega. Then there's the next one, omega prime. Let's also call this omega plus 1. Well, then there's the next one, which we'll call omega plus 2, and then omega plus 3, and so on. And then you can say omega plus omega, and so on. So next page. Formally define addition in ON. Well, recursively, well, by recursion, more precisely, transfinite. Recursion. And so there's 3 parts. So for any ordinal alpha, alpha plus 0, alpha. And for any ordinal beta, alpha plus the successor of beta. I think this is beta plus 1. This is, if you know what alpha plus beta is, then alpha plus the successor of beta is the successor of alpha plus beta. So for 0 and for successors, we defined addition, but for limit ordinals, we need to say that if beta is a limit, not zero or successor, all we do is say, this is the supremum. This is our definition. The supremum of all the alpha plus xi, such that xi less than beta. The supremum of this set. Or, okay, in other words, maybe a simpler way to write it, the supremum over all xi less than beta of alpha plus xi. Okay, I mean, you have to prove that such a definition is valid, but okay, it is. Well, so these first two steps, 1 and 2, this is how you can define addition in omega in the natural numbers. But to go to all of the ordinals, you need this third step. This is an arithmetic definition, let's say, and you can use it. We can prove associativity. Birleşmelik Türkçe'de prove alpha plus beta plus gamma is always alpha plus beta plus gamma by, well, I'll just say, okay, by induction, more precisely, transfinite induction. Because of the three parts, maybe, okay, I won't write it out, but I'll say out loud, you can use these. I mean, it's true when gamma is 0, easily. If it's true when gamma is beta, then it's true when gamma is beta prime. Step 2. And if beta is if delta is a limit, and this is true whenever gamma is less than delta, then it's true when gamma is delta. So there would be 3 steps of the induction, and that's fine. But I won't write this. But let's look by the definition, though. Okay, omega is a limit, so 1 plus omega is the supremum over all xi less than omega. So these are the psi is a natural number of 1 plus xi. But xi is a natural number. 1 plus a natural number is still a natural number. This set is unbounded in omega. So we're looking for the supremum of the set omega. I mean, okay, actually, well, just let's spell this out slightly. It's this supremum of 1, 2, 3, 4, so on, which is the supremum of omega, but by definition, this is omega. But omega is strictly less than omega plus 1. So 1 plus omega is not omega plus 1. Okay, I mean, so addition is not commutative. Toplama değişmeli değil. Okay. Well, okay, we don't get everything, but let's write.
Hocam, may I ask something?
Please.
Is it because omega plus 1 works as a successor and 1 plus omega doesn't work like that?
Well, yes. That's one. I mean, okay, we'll give other their additional understanding. Okay, actually, yeah, let's go through it. What's the geometry of addition? First, okay, let me go back to the reals, right? Because there is a you can define addition sort of arithmetically in the reals. I mean, if okay, if each real number is the limit of a Cauchy sequence, well, you can a Cauchy sequence of rationals. Okay, you can add two rational numbers by the rules you learn in elementary school. So this, you can take the sum of two Cauchy sequences. It's a Cauchy sequence. Its limit is the sum of the limits of the two sequences. So that would be, let's say, an arithmetic definition of addition in the reals. But if you could also, if you think that the reals make up this line, well, okay, let's say, I don't know, A, B, and C. C could be anywhere. We can allow negative. If we think that if AB here, if X is the length of AB, right? You can think of reals as lengths. And the length of BC is Y, but this should be an ordered length, so this is negative. Then X, the sum is the distance from A to C, right? And that's the connection between the arithmetic and geometry. Well, okay, in the ordinals, it's not that easy, but in the ordinals, well, maybe here's alpha and here's beta, right? It's the set of ordinals that came before, right? There's the 0, 1, 2, so maybe beta is greater than 0, greater than 1, greater than 2, and it doesn't contain this, maybe. So actually, there's alpha. Alpha is the set of ordinals less, beta set of ordinals less. How do you add beta to alpha? Well, put the 0 there, put the 1 goes to alpha plus 1, and so on. And here's alpha plus beta. So somehow we take alpha and then we repeat beta after it. And this is the sum. But if you do it for one, so here's one, here's omega. So what's 1 plus omega going to be? So omega contains 0, 1, 2, 3, and so on. Doesn't contain omega. But in the addition, so we take the 0 goes where 1 was, the 1 goes where 2 was, 2 goes where 3 was, and so on. But everything, n goes to n plus 1, but you never reach omega. So somehow the 1 when you start with 1, it gets swallowed up. In fact, Yeah. Hence also for all n in omega. Well, let's say, I mean, n prime plus omega is n plus 1 plus omega, which is by the associativity n plus 1 plus omega, which is n plus omega. So by induction, ordinary induction, let's say k plus omega is omega for all k in omega. It's true when 0, well, okay. We should, I mean, 0 plus omega is the supremum of over xi less than omega of 0 plus xi, so it's the supremum of xi where xi less than omega, so this is omega. Sorry, that's sloppy, but so I mean, this is true when k is 0. If it's true when k is n, then it's true when k is n prime. Therefore, it's true for all k in omega. Okay. So if, okay, I want to say, say f alpha of xi is alpha plus xi, and f, not f, so g alpha of xi be xi plus alpha. Beta is the limit, then f alpha beta, we said by definition, this is the supremum over all xi less than alpha of f alpha of xi, but this f alpha is increasing. You can think of this is the limit as xi goes to alpha of f alpha xi. Sorry, this is not supposed to be alpha, it's beta. We're taking the function at beta, xi less than beta. So the limit of this function at beta is the value at beta. This is continuity. This alpha is actually, I mean, it's continuity is trivial at successors and at 0 because nothing gets close to them. I mean, you think that you have, I mean, 0, 1, 2, and so on. I mean, these approach this limit, which is omega, and then you have discrete points, but they approach this limit, which is omega plus omega, and so on. And it's at such points, continuity matters. But this is continuous. But for example, g omega of omega, okay, this is omega plus omega, which is bigger, strictly bigger than omega, but this is the supremum overall xi less than omega of what we just said, of, well, xi plus omega, but that is g, or we can say this is the limit as xi goes to omega of g omega psi. So the limit of g omega at omega is not g omega of omega. So this is not continuous. Okay, I mean this is okay, this is some of the analysis of the ordinal numbers. Now, maybe there's a question. Anyway, any other questions, feel free. But meanwhile,
There is no question on the chat now.
okay. We said, okay, so every ordinal has a successor, which is bigger. So there is no greatest ordinal. But every set of ordinals has a supremum. Actually, this has a name, the Braley-Forty paradox. So there is no greatest ordinal. But the supremum of ON, every ordinal is in here. So if there were a supremum, it would have to be the greatest. But the supremum of ON would be the greatest ordinal. And also, we said every set of ordinals has a supremum. Logically, hence ON is not a set. The usual way to say that it's too big. It's too big to be a set. Okay, that's the paradox. I mean, it's not a contradiction, but it's strange. It's difficult to understand. This is why set theory is, I guess, a part of logic. When we're doing paradoxical things, we should be careful with the logic so we don't actually make a contradiction. I'll just say, yeah, okay, in set theory, every set A is the class. Every set is a class. Okay, in set theory, I'll just say this briefly. Every set A is the class of all X that belong to A. So every set is the class of its elements. So every set is a class, but some classes, ON is a class, but not a set. Next page. What happened? ON is a class that is not a set. So is, maybe you may know the Russell paradox. There's the class, all these letters stand for sets, right? In our definition, I mean, ordinals are sets. In fact, I mean, in set theory, all these, I mean, these variables all stand for sets, and every element of a set is a set, because that's all you need to do for set theory. But you may see this, the Russell class, this cannot be a set because it's the set of all sets that do not contain themselves. If it were a set, then it would contain itself if and only if it did not. Okay, now, so that's some of the funny logic of these. No, okay. Now we have we've shown how to add ordinals. We've given a formal recursive definition. We've given some geometric understanding of that. Likewise, for multiplication and exponentiation, we did this. So let's see. I mean, multiplication. Well, okay, multiplication in 3 parts. Alpha times 0, 0. Alpha times the successor. This is like beta plus 1, so this is alpha times beta plus alpha, and then if beta is the limit, then alpha times. We define this to be continuous. The alpha times beta is the supremum for all xi less than beta of alpha plus xi. So this function xi goes to alpha times xi is continuous. New page, but okay, yeah, alpha times beta times gamma is alpha times beta times gamma, but 2 times omega supremum over all xi less than omega of 2 times xi, but then xi is a natural number, so this is a natural number. Their supremum is omega, but this is less than omega plus omega, which by the definition is omega times 2. So again, multiplication is not commutative. It does distribute from the left over addition. Okay, you can prove these by induction. Okay, now geometrically, yeah. Okay, so I mean, we gave this formal definition, arithmetic definition, let's say. Again, there's a possibility of a geometric understanding. Well, how do you multiply in the reals? I mean, if you want to multiply, actually, you should go to a second dimension. So this is like the plane. If you say here, if there's a real number a on the number line, this is at 0, but we're going up 0, maybe 1 here, and b here. You've got this, okay, there's this Thales theorem geometrically, which lets us give this definition. If these are parallel lines, the 1 is to A as B is to AB. So this is the geometric definition of multiplication in R. And in, let's see if there's, in ON it will be similar. Let's try this. We have ON, we say maybe here's some alpha, beta. So here's alpha times 1. Okay, alpha times 1 is alpha. I mean, alpha times 0 is 0. Alpha times 1 is 0 plus alpha, or alpha. Alpha times 2 be alpha plus alpha, adding on alpha. So these are, okay, I mean, they're not really parallel. We don't really have the geometry, but there's some kind of idea like this. This is alpha times 2. And then, and actually we're using the associativity here, 3, you get, okay, alpha times 3 and so on. And then ultimately alpha times beta. Or think this way, alpha times 2 is alpha times 1 plus 1, which is alpha times 1 plus alpha times 1, which is alpha plus alpha, and generally. But it has to be in that order, as we saw, 2 times alpha, 2, well, yeah, for example, 2 times omega is just omega. Great, so this is geometric understanding of multiplication. Now, fine, we can go on. What's the next step? Okay, exponentiation. And so it's harder to understand geometrically, but still so more interesting. There's exponentiation. Alpha to the 0 is 1. Alpha to beta prime. It's like alpha to beta plus 1. This is alpha to the beta times alpha. And for limits, beta limit implies, for continuity, alpha to the beta is the supremum over all xi less than beta of alpha to the xi. Here, okay, there's one, if alpha is 0, okay, okay, by the 0 to the 0 is 1, but then everything else is 0, and then this would be 1. It's not 1. So we, that's if alpha is not 0, but 0 to the beta will just be 0. Okay. Well, okay, I mean, this is just, again, the first to define exponentiation for natural numbers, you would use these first two steps, but for limits, you need this new step. What's the geometry of this, so to speak? Again, the geometry, I mean, well, even in the reals, it's difficult. Actually, in some sense, this exponentiation is easier in the ordinals, but to understand it, let's go back to the counting numbers. Well, let's just say let me start by saying so every counting number can be written in base 10. So say 10 to the let's say A1 times B1 plus 10 to the A2 times B2, so on down to some 10 to the AN times BN, where, okay, these exponents are decreasing. Can I write it down here? A1 greater than A2, and so on down to AN. And all the coefficients BK are between, well, 1 and 9. Right? This is base 10. And how do you do this? I mean, okay, at least formally, next page. Given M and N, we find A1 so that, well, 10 to the A1 will be less than or equal to M, less than 10 to the A1 plus 1, or if you like, A1 less than or equal to log base 10 of M less than A1 plus 1. And then the B1, so M is in between, so that's 10 to the A1 times B1 less than or equal to M is less than 10 to the A1 times, well, B1 plus 1. One less than or equal to B1 is strictly less than 10. And M is 10 to the A1 times B1 plus, say, m1, where m1 is less than 10 to the a1. So we start over, we can start, if it's 0, we're done, we know what m is. Otherwise, we start over and we get the next term or the next digit. So maybe I can do this last now. If we can do this with arbitrary ordinals. Well, in fact, even in for any base greater than 1 instead of 10, right? I mean, there's nothing special about the number of fingers we have. You could use base 2, you could use base 13. Everything we said works. Thing is, we can do it in n for any base, say, beta. Greater than 1. That is, for the alpha, for some, well, let's, every ordinal alpha is beta to the, let's say, alpha 1, alpha times, say, gamma 1 plus beta to the alpha 2 times gamma 2, and so on. Beta to the alpha k times gamma k, where alpha 1 is strictly greater than alpha 2, and so on, down to alpha k. And all of these gamma 1, gamma 2, these coefficients, gamma k, these are all between 1, sorry, let me put it this way. They're all less than beta, and they're not 0. So I mean each, so 0 less than each gamma I, which is less than beta, if you like. Okay. Again, the same, I mean, it's the same technique as with the natural numbers. You can find the greatest alpha 1 so that beta to alpha 1 is less than alpha, and then go on. Now, maybe, so I leave with this. Often beta is taken to be omega, and then you have the Cantor normal form. That's pretty convenient. And you can write down rules for doing arithmetic using these things. But maybe I can end with this question. How come the sequence of exponents, I said that alpha 1, alpha 2, I mean, maybe you can like for example, for real numbers, decimal expansions can be infinite. But we had these exponents were decreasing for in our analysis. And ON is well ordered, like omega itself. Every non-empty subset has a least element. And I guess, I mean, you can kind of see that in the construction because every successor, the successor of alpha is the least ordinal, which is greater than alpha. And if you take a set of ordinals, the ordinals greater than all of those have a least element, the supremum. And in fact, if the elements, well, let's not say, if A is a set here, if A is a set of, if everything in A is an ordinal, then the least element of A is the intersection. Meaning, I guess before, I hope I wrote union before. If A has if it contains these ordinals, what's the least? I mean, we've lined them all up well. If the least of them will be just a set of things that are in everything. So I mean, this is sort of xi such that for all eta, if eta is in A, then xi is in eta. Okay. It's been a bit more than an hour, so maybe can stop it there.
I couldn't understand last of point, but actually at the end of the lesson, I want to ask something. Why here we cannot say the minimum of A is 0. 0 is also isn't number of this set.
Well, no, I mean, 0 is a member of every non-zero member of A, but it may not be a member of A itself.
It doesn't have to, you say.
Right, this could be, this, again, I think, for example, I mean, 2 would contain, 2 contains 0 and 1, 1 contains 0, 3 contains 0, 1 and 2, and the minimum element of 2, 1, and 3. Well, is the least element is the set that contains the only common element of all of these, which is 0, which is 1. Okay. Yeah, I mean, this is,
Oh. So the minimum set is the set which contains 0 and it is equal to 1, actually. Is it like
in
that?
this case, that's right, exactly.
Okay.
I
The
know.
definition of numbers in set theory.
Yes.
Oh.
Yes.
Okay.
Yeah, I mean, this is kind of mathematics. I mean, it's so simple on one hand. I mean, but then, yeah, in itself, it's simple, but then it becomes very complicated to us. I mean, let me say the number n is the set that contains 0, 1, and everything up to n minus 1. N is a set of n elements. It's very convenient in set theory and even in notation, but I know most mathematicians don't use it. But well, okay, I think did you have a did you have a talk last year involving cardinality?
Last year, as a
Yes.
seminar, you ask?
Yes.
No, we have a seminar about the set theory, but I was not in the seminar. I don't know which
you weren't there.
subjects they study.
I mean, okay, maybe that would be another time, but we've given ordinal arithmetic here: addition, multiplication, exponentiation. There's also the cardinal arithmetic, right? And this is where you look at size without regard to the order in the sets. And this is much simpler in one sense. But the ordinals, I mean, the Cantor normal form, or generally those expressions in a given base, are useful there, but that takes a bit of work. So but again, I may say again, Cantor normal for every ordinal is uniquely, say, omega to the, say, alpha 1 times n1 plus omega to the alpha 2 times n2, and so on down to omega to the alpha k times nk, where alpha 1, these are strictly descending. And these coefficients are positive numbers, finite, not counting numbers. K is finite. If k is 0, then the whole thing is 0. So yeah, base omega, everything can be written in base omega, and so yeah, you can get rules for combining these things, and yeah. So any other questions?
Another question.
Okay.
I'm checking the chat. It looks like there's nothing.
Okay, then.
Yeah, if you wish, we can end the live session.
I mean, this is mainly, the next topic would be, I mean, I just want to say, if you take, okay, I won't go into this, but this is coordinating. If A is any set, if A is an infinite set, this is the product, right? Cartesian product. This means equipollent or eşlenik. Türkçe'de eşlenik. Bunlar eşlenik. And
is it something like amount of even numbers are same as the natural numbers, because we can write a function one-to-one?
Exactly. So yeah, I mean, that's the next part. And yeah, so but that is, yeah, so when you take, yeah, like let's go to a new page. I mean, 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1, 2, 2, 2, 3. This is like omega cross omega, but this is still equivalent with omega because you can count. This is 0, this is 1, this is 2, this is 3, this is 4, 5, and so on, right? Yeah. So so the point is, this is true for any if A infinite, A cross A is equivalent with A by Cantor normal forms. I mean, the proof, I don't know, the proof I first learned seemed rather, difficult. But if you use Cantor normal forms, it becomes somewhat easier. But I just leave, if everybody knows, think about it. That's an exercise.
Okay.
Okay.
Then thank you very much, sir, for tonight and this seminar.
Thanks for inviting me.
Then good night for everybody. See you later on the other seminars.
Okay, hoşça kalın.